PhD student at UIC, working with Professor Yao. It is a pleasure to be here and have the chance to share our recent work with it is accepted by CVPR this year. So today I'll be talking about our work regarding large angle camera redirection from a monocular video. So you have already seen this video clip from Charles' presentation. It's quite an iconic bullet time effect for movie industry. But how is this effect created? The basic idea is to place a dense ring of synchronized cameras around the subject. But this camera ring for bullet time is hard to scale. It is not scalable to outboard large-scale scenes or moving objects. So this naturally leads to the main question of our work. Can we create bullet time from just a monocular video? Monocular videos are quite easy to obtain from your daily life. You can shoot everything with your phone. Previous works mainly fall into two paradigms: explicit warping or implicit control. For implicit control, they usually encode the camera trajectory or text prompt as embedding to the denoising process. But the problem is, it's quite hard to control. For the explicit warping, what they do is they usually use the depth estimator to lift the 2D video to the depth map, and then warp the observed content to the target trajectory. Because you only have the observed content, so the camera here is not complete. You only have the partial one which you observe from the initial video. This motivates our key idea, using the explicit geometry, but a complete one. So at a high level, our pipeline has three stages. The first one is the decoupled reconstruction. Here we have the background reconstruction together with the foreground object completion. And then in the second stage, we align them together to get a 4D proxy. In this phase, you can arbitrarily define your wished target camera trajectory. And then we render the depth map, which served as a geometry guidance for the next video generation part. And together with the text prompt and reference image, we get the final video. You see, in this kind of this example, the car here is occluded by the trees in the foreground object. And the main point is the whole pipeline is training free. So let's first look into how we complete the object here. So from the initial video, we have the master video, use SAM. And then we use a multi-view video diffusion model to generate 4 different perspectives of this dynamics. And for each frame, we have a vigility inference to get a point cloud. And for the whole sequence, we get a continuous moving dynamics point cloud, which is also complete camera view. For the background, we just put the original video to a dynamic aware feed-forward network. And we get a background reconstruction together with a partial camera here. The camera here is not complete. You only see the part of it, which is from the original video. And in the third part, because we have this masked video from the original video, which we share same pixel-wise coordinates, so we have these 2D correspondence. And these 3D point clouds are derived from the 2D videos via depth map. So you have pixel to point cloud depth map correspondence. And we raise this 2D correspondence to 3D and align this complete camel back to the world coordinates. And in the end, we have this background reconstruction together with this complete camel in the whole workspace. And with this complete camel, you can get arbitrary target trajectory as you wish, and together with reference image and text prompt, you get the final video. So back to the robot example. Starting from this input video, we can really generate a bullet time style replay. You can see both the robot motion and the office structure are well preserved. Here's another qualitative result. Compared to the baseline, our method shows more consistent human motions rather than distorted or blurred objects. We also have some quite interesting applications here. The first one is the appearance propagation. Here we only added the single reference frame, for example, by changing the texture or applying a style transformation. Our method can propagate this edited appearance consistently across the generated target video in the new views. And the second application is the geometry editing. Because the representation is explicit and point-based, we can directly manipulate the underlying 4D structure. For example, making the car smaller, or even combine a camel to the BMW mini cars things, which is hard. This kind of effects is really hard for the learnable or data-driven methods. So to summarize, we present a training-free framework for polytype style camera redirection from single monocular video. Our key idea is to build a geometry-complete 4D proxy before video synthesis. This enables more reliable large-angle replay and downstream editing applications. And one more thing is, we all know 4D data is quite expensive and hard to obtain. So leverage our pipeline, we collected some YouTube videos and build their Studio 4D branches, just like this. This video we downloaded from YouTube and set up a benchmark for camera redirection. And code and data are all released. Welcome to check our project page. Thank you.